Okay, so let's finish the discussion of section 2.2. So this is section 2.2 continued, still talking about graphs of functions. And we had a few more things to discuss here. Just to recap real quick, we had power functions, functions of the form f of x equals x to the n, and we said that in general, like with no other stuff, no negatives going on here, nothing else going on with this function, just an x raised to some power. We said that in general, the shape is going to be like this. Oops. If n is even, so this is for even n values like x squared, x to the fourth, x to the sixth, etc. Both legs pointing in the same direction, in this case both pointing up. And then we had the odd functions, or rather the odd exponents, so with odd values of n. Okay, then we had the next class of functions we looked at were those root functions. So these are so-called up here, these are so-called power functions. So if I just gave a name to each category here, power functions, and then these were the so-called root functions, where that n is in the index position. So these are root functions. And we had that these were a bit different. They're sort of like a sideways version of these, and that like I've alluded to before, there's no coincidence, or that's no coincidence, but we'll discuss that more later. When n was even, we had a sort of half of a sideways parabola, sort of like this case on its side, but only half of it, right? We only want half of it, and that is to make sure that we're maintaining that definition of a function here, that it should only output one output value. In other words, only one y value should be outputted, right? If I plug in 4 into this, square root of 4, if it's a square root, square root of 4 should only be 2, not 2 and negative 2, right? Only one y value per input value. And also, this thing did not allow negative values plugged into it, right? So there was more to say about these root functions. Then when you had n being odd, so an odd n, you can have negatives plugged in, and it very much does just straight up look like a sideways version, sort of odd valued power function up here. So this is an odd root function there. So this might be like a cube root of x function or a fifth root, etc. So we already discussed these. Just as a extra little bonus thing here, the domain of power functions for all of these, here I'll write the domain for each of these in blue. The domain is completely unrestricted. Oops. Negative infinity up to positive infinity. That's a parentheses there. We always use parentheses around infinity, right? And then over here, same deal. There's no problem plugging in any x value you want into a function like this. You plug in whatever you want. Plug in negatives. In this case, if you plug in a negative, it spits back out a positive, right? And in this case, if you give it a negative, it outputs a negative. Now over here, though, we had to be a bit more careful. This one, the domain, you have to cut it off, right? You cannot allow negatives under an even root function, like a square root or a fourth root. Most common ones, right, are square roots, right? So we don't want to allow negatives under there, and the way we do that is we say, okay, you're allowed to plug in 0 and all positive stuff, but not anything below 0. Over here, though, no problem. Oops, I forgot to write D for domain. D for domain is okay. So far, the only one with any like weird domain is even root functions. By the way, all this data, actually they don't mention the domain, but on page 202 in the text, they have nice pictures of all of these categories, including another category that I'm about to go into right now. Okay. So what if I have a function of the form f of x, and what's the other kind that I started talking about in section 2.1, and I used it as an example of a function that had a restricted domain, the 1 over x functions. And in fact, we're going to look at them the same way we've been looking at these other categories, with a power of n attached. With the power of n, and you're going to see that they're going to fall into two different categories, with n being even and odd, just like the other ones. There's going to be two like subcategories, and these are called reciprocal functions, or you could also call them rational functions. They're part of a broader class of rational functions. Reciprocal here just meaning they're like the multiplicative inverse of stuff like this. Instead of just x to the n, it's 1 over x to the n. When I say a rational function, the words rational function encompasses like even more functions that can have other x stuff going on up top. When it's just got like a 1 on top, or maybe just some non-x, like just a number other than x up top, and the variable is only in the denominator, we consider it a reciprocal function. What are going to be the shapes of these? So we already know there's going to be some domain issues to consider, because I can't have a 0 in the bottom in any case, right? It doesn't matter if n is even or odd. Can't put a 0 down there. Let's consider 1 over x. So I'm just going to do it the same way we built up the other ones. Just start off with a table of values. So x, and we'll start with n being 1. So that means just 1 over x. There's my function. You could put just f of x equals 1 over x here. The point is I'm starting with n equal to 1. So that exponent on the x in the denominator here is just a 1. So I've got x and 1 over x. Now those classic values to pick are -2 through 2. So maybe I'll just kind of naively start with that and just see what happens. I mean, the worst that can happen is it's a bad table of values and I just have to start over. That's not too awful. So if I put a -2 in the bottom here, I'm going to get -1/2. -1 in the bottom here is 1 over -1, so I'm just going to go ahead and call that -1. 0 in the bottom, that's undefined. That's okay, you can write that undefined. 1 over 1 is 1, and 1 over 2 is 1 over 2, 1/2, right? 1 over 2. All right, so if I did try to graph these values, so far, what would it look like? So I'll, okay, I'll make a graph here. Oh, what am I doing? I can use Desmos. I'm thinking since I'm recording that I don't have access to like, you know, Desmos and stuff, but give me 1 second. I will pull it up and then I can share my screen since I'm actually recording this in Teams. Desmos. All right, so you can see this thing. What do we call it? Graphing calculator. All right, so real quick, I'm going to build a table of values. Whoops, which is kind of a cool thing that you can do in Desmos. Now, of course, if you want to know what this function looks like, you would just type in the function. You won't make a table of values, right? Oh, it's mad at me. Oh, I know. Hang on. Subscript. There we go. Okay, so now our table of values should look the same as what I gave it, right? We had -1 over 2, which is -0.5, -1, undefined, 1, and 0.5. All right, so over here are these 4 points, right? Because the middle point is undefined, so it tells me nothing. So this looks kind of weird. Like, what is going on? What is going on, right? This like just how do I connect these? Are they supposed to be connected across 0 because 0 is undefined? So maybe what I'll do is I'll add some values here. And let's see if I can just, I don't want to do that. I just want to add more. There we go. I'm going to add some more values into my table. What I'd like to investigate is I'd like to investigate what's happening as I approach that 0 value, because 0 is where everything just goes crazy, right? And whenever you've got a function like this with an undefined spot, a good technique is to try to get close to it to see what happens. So if I get close to 0 from this side, so this is x equals 1, right? This is the point 1 comma 1. So I want to get I want to go further left here without crossing 0. I don't want to get at 0. So what's a good number to pick between 0 and 1? Well, how about x is 1/2? So this time I'm going to plug in 1/2 into as an input, and there's that new point. There's that new point right there. Okay, cool. So what if I go even closer? What if I go between those two, 0 and 1/2? What's in between those two? About 1/4. Okay, so now we're starting to see this kind of shape where as it gets closer to 0, it's gaining speed really fast going upwards. And since we're doing this on a computer, I can even like go for, how about like 1/, what's between 0 and 1/4? How about 1/8? And it's not even on here. I'd have to scroll up. Where is it? There it is, all the way up here. So that's the coordinate point, 1/8, which as a decimal is that 0.125. And then the output, we see the output is 8. Does that make sense? Well, look at what happens over here with, if the input is x, and then I take the reciprocal of this. So what's the reciprocal of 1/8? Well, it just means you flip it, right? And when you flip 1/8, you get back to a whole 8. Okay, so that's what this function is doing. You give it tiny fractional values, and it starts to output big whole number values. So if I gave it 1/100, it would spit out 100. All right, so that's what's happening over here. What if I approach 0 on the left-hand side? So between 0 and -1. So I'll just like take these values and put negatives in front of them. So I'll try -1/2. Okay, that, I don't know if you saw that, but it added this point right here. Now I'm going to try to add -1/4. So I'm just kind of mirroring those values that I picked for the positive side, and then I'll do -1/8. So you see it, these are the 3 new points I added, and there they are represented. There's -1/2 as the x value, -1/4, 1/4, and -1/8. respectively, giving outputs of -2, -4, and -8. So we're kind of getting an idea definitely about what's happening near this y-axis where x becomes 0. Okay, what about when we let x get very large? What's happening here? Is it gonna go down here or something? Let's investigate more. So we have well, let's see. This is x equals 2. Let's just pick a really large, well, not super large, but let's pick x equals 5. So there's that point. 5 and 1/5. That's the out. 0.2 is the same as 1/5. Cool. So, and that's pretty much what it's going to keep doing as we go further out. So like if I pick x equals 10, its y value, its output is 1/10. In other words, 0.1. So, sorry. So that's what's happening as we let x get large this way. And the last direction that we haven't really investigated is x getting large to the negatives. So I'll just, these 2 positive values that I picked, 5 and 10, why not? I'll just make them negative to see what happens on the left. -5 and -10. And it's kind of like a mirror image happening on the other side. But notice it's not touching the axis, right? And it never will. If I zoom in enough, there's a big gap here. This is the point -10, -0.1. This graph, zoom out more, will never ever touch either of the axes, even though it looks like it gets pretty close. Okay, so now if I go to a new, just for the sake of having a clean image, and I just straight up go 1/x and I don't build a table of values, here it is. This is the function. This is the function that we just mapped a bunch of points. See, we mapped a bunch of points to, and now Desmos is just straight up telling us this is what it looks like. So why didn't I just show you this from the top? Well, because I want you to get an idea of how the values are working, how it's called a reciprocal function because it takes in inputs and takes the reciprocal of them. If you give it a 5, it gives you 1 over 5. If you give it 1 over 3, it'll give you a 3. So like if I go find, if I graph the point with an input of 1 over 3, it should give me an output of 3, and there it is. There's that point, 1/3, comma 3. It's a reciprocal function. All right. So, sorry, let me get back to, here we are. All right. So we use Desmos to help us see that for x equals 1, we're going to have, now see, it's going to be harder for me to do on paper, but this kind of general shape. And the point is it should not cross the axes. Oof. And it should be a mirror image around the origin. It's symmetric. It's as if this little spot here, like there's a mirror, like diagonally down here, there's a mirror, and it's a mirror image of itself. And it never crosses the horizontal axis, the input axis, which we like to call X, and it never crosses the vertical axis, aka the output axis, which we like to call Y. It never crosses either of those. Now, this is going to be the general shape for reciprocal functions when we have an odd value n. And I'm going to show you that now in Desmos, and then we'll investigate even ones. If I could find it. All right, there we go. All right, let me erase that. So there's 1 over x. Here is 1 over, so we're investigating odd ones. So there's 1 over x cubed. Oops. Whoops, 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 whoops. There's 1 over x cubed. 1 over x to the fifth. So you see they all kind of have the same general shape where it's like an L thing happening in the first quadrant and a weird upside down L looking thing in the third quadrant. Notice though that so there's the red one and then the green one. As we get higher in the exponents, but maintaining that they're odd, they get something is changing, right? They're getting further from the well, how can I say? They're getting like more squarish, right? Like the first one's pretty curved. It's like a curved L, but by the time I get to x to the fifth, first of all, it gets really close to the x-axis really fast, right? It looks like it's touching it. It never will. It still never will touch that 0 point because it can't have 0 as an input or output, rather. But it gets really close really fast. And if I just say, like, how about I pick a really big odd number, like to the 73, and look at that. Yeah, I mean, it almost looks like a right angle, right? It almost looks like a right angle. But of course, if I zoom in far enough, I see that it is curved. But if I zoom out, but the point is, kind of the main point is that with odd exponents, you're getting that same like L shape here and L shape here. And that's what I need you to be able to recognize. I need you to be comfortable with 1 over x and 1 over x squared, like actually being able to graph those. And also just knowing that the odd and even functions kind of look generally the same as those two categories. So with that being said, we need to investigate 1 over x squared now. So if I go back to, nope, hang on. There we go. If I go back over here and I just change this to be, well, I don't want to give it away. Let's see, can I delete? I want to delete some of these. Ignore where it's saying undefined. Oh, there we go. I want to do the same kind of 5 values here. So let's go ahead and say 1 over x squared. I want to talk about what these are because it's just telling us. If I plug in -2 into 1 over x, in fact, you know what, let's do this on paper and then we'll come back to Desmos. Let's do this on paper real quick. So let's get caught up with what we're doing in Desmos here. So f of x equals 1 over x squared, and we're going to say table of values, x and 1 over x squared, -2, -1, 0, 1, and 2. Okay. -2 plugged in here is going to be 1 over -2 squared, right? That's how that works. That first input, that should be 1 over 4. Okay. 1 over -1 squared. -1 times -1 is 1. So this, long story short, just gives a 1. 1 over 0 squared, well, that's undefined. All of these reciprocal functions are going to be undefined at 0, unless you've messed around with the bottom and like scooted it around, but we'll talk about that later. 1 over 1 squared is still 1, and then 1 over 2 squared will just be 1 over 4 again. So we're seeing symmetry again here where it's only outputting positive, so it's like symmetrical here. 1, 1, 1/4, 1/4. All right, so now let's go look at Desmos. So it's already calculated those 5 values for us, and keep in mind it's giving us the fractions as decimals, so 1/4 is 0.25. Now, these are the 4 dots we're given. That tells us like nothing, right? I mean, this could be anything. So let's get some more values. We'll do the same thing where we investigate numbers getting closer here. So let me try an input of 1/2, and let me try an input of 1/4. Okay, so 1/4, I see the output is already at 16. So I think I'm not going to go any further than that because they get big really fast. So there's the 1 over 16. I mean, 1 over 4 in the input and an output of 16. Why is it 16? Well, because if I reciprocate this, it'll become a 4, but I'm also squaring it, right? Because that's what the function does. It's squaring it, and 4 squared is 16. Let me investigate those same values on the negative side, and they should give me the same outputs. They do. They do give me the same outputs. 1/2 yields a 4, -1/2 yields a 4. 1/4 yields a 16, -1/4 yields a 16. And what does that mean for our picture? It means those points are like mirror images of each other around the y-axis. So here's the 1/2, 1/2, 4, that's this point. And then this point here is -1/2, 4, that's this point. And that's okay, that's still a function. You can have 2 different inputs going to the same output. That's okay. You just can't have the opposite case of 1 input going to 2 outputs. That's what's not allowed. Okay, so let's investigate some points. We've investigated up the, or getting closer to 0. Where is that other point? There they are, all the way up there. Let's investigate as we let x get very large. So I'll just say like x is 3. Okay, there's that new point, and let's say on the others, let me do like, actually, I'll do a 5 like I did last time. There's 5 and 10, and then -5 and -10. Just picking random variables that will kind of stay on the page here. Or not variables, sorry, random values. Okay, so we're seeing this kind of general shape here where it looks like an L on this side and an L on this side. So it's very similar to 1 over x squared in that they're both kind of this L shape, but now they're in the first and second quadrant. They're symmetric around the y-axis now. And we'll see that here when I graph it. So there it is. Oops. There's 1 over x squared. Okay. And all of the even functions, all of the even exponent, what am I trying to say? All the reciprocal functions with even exponents are going to have the same general shape, an L over here and then a reflected L over here in the second quadrant. And as I let that value get larger and larger in the denominator, they are becoming sharper and sharper shaped. So there's red is 1 over x squared, blue is 1 over x to the 4th, and then the green is 1 over x to the 6th. And then if I pick a really big value just to kind of emphasize what's happening here, like 1 over x to the 72, you see, I don't know why it's making these all. Hang on one second. Make that orange there, or purple stands out maybe a little bit better. No. You see how when it's a very, very high exponent, they get very sharp. Okay, but what's the point? What do I want you to know? Because I don't need you to know, you know, specifically what the graph of 1 over x to the 72nd is. It's really about knowing that when it's a reciprocal function and the exponent is even, you should expect a shape like, oof, that's ugly, like this. L over here looking thing, and then an L in the second quadrant. Not crossing the axes. That's a big point to make too. Not crossing either of these axes. It's not touching the axes at all. And this is for when n is even. So that's the last class of functions that we're looking at in 2.2. We're going to continue looking at these functions and how we can start scooting them all around the coordinate plane. But first, let's finish a few more ideas in 2.2. We've got namely the, what do we got? I knew there was something else. I didn't want to talk about piecewise functions. Oh yeah, the vertical line test. This is really nice. Because it should tie into our definition of a function very nicely. Sorry, I'll be right back. Give me 1 second. All right. Sorry about that. Needed water and forgot I cannot pause these recordings when I record them in Teams. So, okay, vertical line test for functions says, well, first of all, let me remind you about the definition of a function. What is not allowed? Sorry. One input. That's what's not allowed. One input going to two different outputs. Like for example, f of 2 equals 1 and f of 2 equals 3. That's not allowed. Why? Because that's one input, namely the 2, going to two different outputs. Not allowed. Okay, so how does this translate to a picture? How does this translate to a picture? Well, say I've got some curve on a graph that's supposed to represent a function, maybe or maybe not. How do I know if it represents a function? Well, what if I have a curve that does something like this? I don't know, something like that. This is not a function. How do I know? How do I know? Well, because I see that if I pick the right input value, like something here, that I'm getting two different output values from this function. Remember, input values are coming on this horizontal axis. Output values are coming from this vertical axis. So I'm getting an output value here at the same input, right? And then another one down here. Whoops, oh my goodness, there we go. There we go. So I'm getting for some input here, which might be like, I don't know, I'll just make up a number like 3. If that's x equals 3, then these 2 points here are like, maybe this one's up at, so f of 3, right, that's the input. Maybe I'm getting like a 2 there, so that's like a 2 up here. And then down here, like a negative 1. So I'm getting this thing, these values coming from this picture. Just assigning numbers here just to help you kind of make sense of this. But the point is, if you pass a vertical line through a function and it hits in 2 places, what does a vertical line represent? What does a vertical line represent? It represents a whole set of, or rather, it represents one input value, right? A vertical line represents some x value all the way up and down the coordinate plane. So if you're picking an x value like 3 and you're looking up and down x equals 3 and your function is hitting more than one output value, then it's not a function. You know, I mean, you can still graph it and talk about it, but it's not a function. Hence, the name of this test is called the vertical line test for functions. And it says, so if you pass a vertical line through a, I'll call it a curve, right? Because it's, I don't know if it's a function yet. So just a generic word, curve, or graph of a line or whatever it might be. If you pass a vertical line through some shape on the graph on a coordinate plane, and it hits in more than one place, then that shape, which I'm calling a curve, is not a function. Okay. All the shapes that we've talked about in 2.2 are functions. Because if I pass a vertical line through them, I'll only hit them in one place, right? Some of them get kind of close because they get steep, but they're definitely functions. All of these are functions. Same for the, where are they? These guys, right? They're all functions. They don't double back on themselves, okay? Different to this thing that I drew here. This thing I drew here doubles back on itself, so it's not a function. What are some classic shapes that we have talked about that are not functions, that we've actually graphed that are not functions? How about the circle? Right, circle graph. Sorry, that's a really ugly axis there. So this is some circle with some center here and then some radius. And in fact, I could even say, just to remind you, like a quick review about what the graph of a circle looks like. It's if this center is at 4, 0, so x value of 4, y value is clearly 0 because I'm on the x-axis. And let's say it's got a radius of 3, then its equation would be x minus 4 all squared plus y minus 0 all squared, but that would just be y squared, equals the radius squared, so 9. Anyways, that's just a quick review of equation of a circle in case you forgot. The point of it, though, the point I'm trying to make here is that it's not a function because I can pass a vertical line through it and hits in 2 places. So circles are not functions. And that's okay. I mean, we can still talk about them, but if you want to define a circle to be a function, you're going to have to do something where you restrict its domain or something, or its range. You're going to have to restrict it somehow and only take, you know, like part of the circle, maybe just half of the circle. In fact, that's a good point to bring up that square root of x function. So let's consider that problem that we were talking about before. Because there's a lot to say about this square root of x function. As an equation, like if I have y squared equals x, and then I say as an equation, if I'm solving for the output y, then y would be equal to plus or minus square root of x, right? That's how we all understand to use it as an equation. If I graph this as an equation, I can do that. I can say as an equation, this graph would look like, it would come in two pieces. The so-called plus part would be just like what we are used to as a square root of x graph, so it would look something like this. And then the minus square root of x part, so it's coming in two pieces here, would be reflected over the x-axis. It would look like this. But the problem is, and this is well, and that's fine, you can graph equations of two variables. That's what we did in section 1.2. But the problem with this is it's not a function, right? It's not a function because it breaks the vertical line test, or it fails. I suppose I could say it fails the vertical line test, right? So when we decide to talk about the square root of x as a function, we all agree to not take the negative values that it can possibly output. We all agree that, so this is equation form. We all agree that to make a function out of it, we'll only take that positive side. The positive side, so that it does pass the vertical line test, because now I can pass a vertical line anywhere through this function. It doesn't matter where, and it's only going to hit one spot, right? It's only going to hit one part of the curve. So this is not a function because it fails the vertical line test, and this is a function. So we restrict it so that we can talk about it as a function. And why do we agree to only take the positive side? Why not just take the negative side, like just this? Well, because it's easier to talk about the positives. Like honestly, like I think that's the only reason. It's just easier to deal with positives than negatives, right? I can't think of a reason really, honestly, other than that, why you couldn't just restrict it like this and only take the bottom half. It's just way more natural to just want to take the top half of it. Okay. That is it for 2.2, but I'm going to keep going into 2.6. So we have, we're skipping 2.3 and 2.4. We're just straight up not going to talk about those. We are going to talk about 2.5, but I like to do 2.6 before 2.5 because 2.6 is all about the functions you just learned about and about transforming them on the coordinate plane. So the order of things is going to go 2.1, 2.2, 2.6, then 2.5, and then 2.7 and 2.8. I know that's kind of weird, but if we didn't, as a course, if we didn't skip sections 2, 3, and 2, 4, it would make more sense to me to go straight just like in the order they give. But since we do jump straight from 2.2, it makes more sense to just go ahead and move straight into 2.6. So that's what we're going to do here. Transformations of functions. Okay. How much can I sum up here all at once? If we add If we add or subtract to the quote-unquote outside of a function, then we scoot it up or down. What do I mean by that? If I take a function graph f of x, so here's an example, f of x equals x squared plus 3. All that's going to do to my function, and I have to know what x squared looks like here, okay? What's that going to look like? X squared is a parabola shape, right? Like a U kind of shape. And the plus 3 is just going to take that parabola shape and shift it up by 3. So if that's 3 right there, just kind of arbitrarily putting a 3. There's 1, 2, and 3. It's kind of ugly. And then just draw the parabola from right there. Okay. If I subtract, then we should expect it to shift down. So how about x squared minus 2? So what I'm doing is I'm taking like the output that it would normally give, and when I add 3 to the quote-unquote outside, meaning not in next to the x, but literally like as an order of operations, I do this part first and then I'm adding 3. It just results in a vertical shift. A vertical shift is what we're going to call it. So here's a picture of the second one. Maybe there's -2 right there. And I'll just draw my parabola, just starting from that -2y value. Just like that. So the point is that I'm adding or subtracting to the outside of the function. This addition or subtraction is happening after I square the values. Okay. This is how it's going to be for every single type of function. How nice is that? This rule holds for every type of function that we're going to look at. It holds for any type of function at all, really, especially as vague as I put it there, but anyways, especially for the functions we're going to look at. So if I write this rule in more generality, here's how I'd write it. Oof. Or not more generality, but more technicality is what I mean to say. Given a function f of x and a number c greater than 0, the graph f of x plus c is vertically shifted up. Vertically meaning this way, right? Vertically shifted up by c, and f of x minus c is vertically shifted down by c. literally adding or subtracting to the outside of the function. So if the function, original function is x squared, then the new one could be like x squared plus 3 or x squared minus 3 or something like that. So let's go look at some examples on Desmos because it'll be easier to see them here than to try to watch me draw them. So let's start with a base function of x squared. Now I'm just going to start adding and subtracting stuff to it. So here's x squared, and then I'll say, let me change the color. Let's make it red. Yeah, red. Green will stand out more. Okay, and let's say plus 5. Okay, where is it? Well, it's up at 5. There it is, at 5. The origin of it is now at 0, 5. That y value has increased by 5. You see, this one's origin is at, like, when I say origin, I mean like that maximum lowest point of the parabola, sort of, which you might think of as like the starting point, though it's infinite in either direction, so it doesn't really have a starting point. But if we point it at a starting point, that would be the most natural point to point at. And when you add 5 to the quote unquote outside of the function, like I've done here, adding to the outside of x squared, it lifts that y value by 5. You see, it's lifted it vertically. And what if I had like x squared minus 4? There it is. Its y value is now at -4. So there's all those y values. So you can see the base one's at 0, this one's at positive 5, the green one, and then this one down here at -4. Now, what about if I say x to the third? Let me change all these to. So there's your base x to the third graph. Right, remember that, it's like this kind of shape. Got to remember what that shape is. And then what if I add 5 to that? See, just lifts it by 5, lifts that kind of central point of it, 0, 0, up to 0, 5. Lifts it straight up. Everything else about the graph stays exactly the same. It just lifts all of its y values up by 5. This one drops it by 4. Because I subtracted 4 to the outside. So it's dropping all of its y values by 4 from the base purple case. Okay, it works for the square root functions. I guess I should say just the root functions in general. So here's the square root of x. Square root of x plus 2, say. Vertically lifted. I can even drop square root of x into the lower. I can drop it lower too, like -7. Put it all the way down there. See, all the way down there. So its origin, this one does have a starting point, right? 0, 0. That's the base graph. Just make this more clear, make it red. All right. There's the base graph at 0, 0. If I add 2 to the outside, that adds 2 to the y value there. And then corresponding down here, if I subtract 7 to the outside, it drops that y value by 7. It's dropping all the y values by 7, but this is really a nice one to point out, right? This one very clearly dropping by 7 in the y value. Okay, what about a cube root of x graph? Oh yeah, I gotta remember how to do this. Let's see, it was under functions and then miscellaneous, nth root, cube root of x. Ah, okay, there's cube root of x, cube root of x, cube root of x. Okay, there we go. Sorry about that. Okay, there's the cube root of x, base graph, cube root of x. And then what if I add 4 to it or whatever? Add some whole number to it just to make it easier. There it is, lifted up by 4. Lifted up by 4. Okay, and then what if I say -4? Oop, where is it? There it is. Okay, so this rule is working so far for all the functions, and the final thing to look at is the reciprocal function. So I'll look at 1 over x. Now I need to be careful here how I write plus. It needs to be out here, so maybe +2. Now let's really consider these a little bit more because these are a little bit weird. Something that can be helpful is to, when you're transforming these reciprocal functions, when you're moving them up or down, or later we're going to look at moving them left or right as well, is to think about where that asymptote went. So the values where it never touches are called asymptotes. So right now, this blue graph, the base 1 over x graph, has a vertical asymptote on the y-axis. Now that won't change when we lift it up or down, but it also has a horizontal asymptote on which is right at the x-axis right now. But when I lift it up, that asymptote is moving, and it would be really helpful to have that written down so I knew, or drawn on the graph so I knew where to put it. So what you can say is that if you know you already have an asymptote on the x-axis, that's at y equals 0, right? Y equals 0, that's the x-axis. And I'll denote it with a red dashed line there. So that's the horizontal asymptote for this base case. Now, if I want to be able to figure out where is that asymptote going to be for 1 over x plus 2, because maybe I want to graph 1 over x plus 2, and I'm sketching it on paper, but I'm not sure like how high it should be, like how this should look. Well, its new asymptote is just going to be at y equals 2. You're just going to lift that value by 2. I'm going to make it red again and dashed line. So there's the new asymptote. Maybe I won't make it red. I'll make it orange. And now I know that my graph should not touch that orange line. It should get very close to that orange line over here and get very close to that orange line over here, but never crossing it. And there it is, that green. So let me get rid of these now. That green function is the lifted one. And then maybe I want to take 1 over x and subtract 5, maybe. Color's not being used, green. Okay, how would I know where to put that horizontal asymptote? Well, it would be at y equals -5, just dropping the y value from y equals 0, where the base horizontal asymptote is, dropping it by 5 because I'm subtracting 5, right? So that new one will be right there. Let me get rid of that and that. There it is. That's 1 over x minus 5. You see how having this dashed line at the horizontal asymptote could be really helpful for figuring out where your graph should be going. Okay. That's the first rule for vertical shifts. Here's the next rule. If we add or subtract to the inside of a function, then we scoot it not up or down, we scoot it left or right. Okay, what does it mean to be on the quote-unquote inside of a function? Well, let's consider f of x equals, I'm going to just use a parabola because a parabola is like the nicest case. It looks the most common and like it's a good case to look at. So maybe x minus 3 all squared. And then let's also look at f of x equals x plus 1 all squared. That's what it looks like to add or subtract inside the function. Inside the function. Like literally the operation is happening right there next to the x, and then we're getting squared, right? So the base function here is still x squared, because if I take, if I take these extra operations away, it would just be, these would both just be x squared graphs. What are these going to look like? Well, what these do, I've already said they scoot left or right, so we know it should be a parabola somewhere on the x-axis. The question is, does -3 scoot it left or right? Right, so it should be by 3, but is it left or right by 3? And it's going to be to the right, towards the positives, which might be a little counterintuitive, but let's see, how can I say? Think about where the 0 point, the origin of this parabola would be. The origin is going to happen somewhere on the x-axis where the y value, the output value, is supposed to be 0. What value of x is going to give me an output of 0 here? Well, a 3, right? So that's where the origin is going to be. So it's going to be over here, 1, 2, 3, at the positive 3. That's a positive 3 there. And that's where my parabola is going to be based. Oh, that's pretty ugly. Sorry. Okay, so originally a base parabola would be right here at x squared. The base parabola of x squared would be right here at the origin at 0, 0. But now its new little origin point is 3, 0. 3, 0. Kind of the same thing going on like we had for circles, where if you wanted if your center of your circle is at 3, 2, then that's reflected by minus signs in the equation. If you remember that, that was a little counterintuitive there too, and it's kind of a similar thing happening here. So likewise over here, we're going to have a parabola right there at -1, because a +1 inside is going to shift it left by 1. There we go. And its new little origin point would be -1, 0. Notice the outputs of both of these, or the y values, are still 0 because it hasn't lifted up or down. Okay. Only left or right. This works for all the functions. I encourage you to go play with all the functions and just add or subtract inside each of the functions, and you'll see them scooting left or right. Okay, I'm going to write down the technical rule, and then we're going to do some examples on paper together. It's going to kind of mimic this rule. In fact, I think I'll just write it on the same page. How do I notate something being added or subtracted inside? Well, I literally put it inside like that, inside the function. Okay. Given a function f of x and a positive number c, f of x minus c is horizontally shifted right, and f of x plus c is horizontally shifted left by c, which is what we just saw with those two parabolas. So now, let's put some examples together. Rather, let's do some examples that put these two transformations together. Example 1. f of x equals x minus 2 all squared plus 1. So I'm thinking that this should be, maybe it's helpful to draw a little tiny sketch, like not on a graph, so it's, there's not a big commitment here. I'm thinking that we should have a parabola scooted right by 2 because of the minus 2 in there, and up by 1. Up by 1. Okay. It might be helpful to consider then, where is its origin going to be? If it's there's going to be special points on each of these graphs that are going to be helpful to consider as kind of like a base point for you to start from. And for the parabola, it's definitely going to be that point. I'll just go ahead and tell you, on a parabola, it's called the vertex. The vertex, which for a base x squared parabola is just 0, 0. So if I'm shifting it right by 2 and up by 1, then its new point, its new vertex is going to be 2, 1. Shifting right by 2 increases its x value by 2, and up by 1 increases its y value by 1. Positive increases for both of these. There's going to be points like that that are helpful for each different type of graph. That help you get a kind of anchor point for where you should be going. And for the reciprocal functions, it's going to be finding those asymptotes instead of an actual coordinate point. So let me go find the point 2, 1, which will be right there, 2, 1. And then from here, I'm just going to draw a parabola. Like, I'm not going to worry about other points it goes through. Kind of the point of getting the idea of the shape of these graphs is that later, when you're graphing things like this, you're not super worried about where, what the rest of it looks like, as long as you get the general shape right, and also that original starting point there, that sort of anchor point. As long as you get that point right and the general rest of the shape of the graph right, then we're good. Okay, how about g of x equals x plus 1 cubed plus 1, like that. Okay, little mini sketch to start off with. I know my base x cubed graph, I just have to bring that knowledge to this problem. I have to bring the knowledge that this is my base x cubed graph there. Also, I should note that a nice special point to consider is that 0, 0 point where it sort of changes direction, where its shape sort of goes from pointing down to pointing up. And I'm going to be moving it left by 1 because of that plus 1 inside, so that's left by 1, and up by 1, just like the last problem, up by 1 because of the plus 1 outside of the base function x cubed. So my new graph is going to have the same general shape, except that little origin point there is going to turn into left by 1 means I'm negating or going to the left for the x value, so -1, and up by 1, so that y value will still be +1 there. Okay, so come over here and graph that. I'm going to find that point -1, 1, which will put me in the, oops, no, sorry, it's not down there, it's up here in the second quadrant at x equals -1, y equals +1. So that's sort of that point, that's that point right there on the graph. So from here, I'm going to go like that and like that. There it is. So it was right here, right? It was here at the origin, but then I shifted it left and up. Okay, let's do a root example. Let's see, wait, was it? Yeah, so still same example. So from scratch, how do I do this? Well, not completely from scratch, but if I was you, how should I approach this problem as a student? You have to come into it with knowledge about what the base graph square root of x looks like. So you're taking away these extra operations, the -4, the -2, square root of x, I have to know that it looks like that. I should also know that that sort of special starting point there is at 0, 0. What's the next thing I need to know? I need to know what the -4 does. -4 is inside the function, so that corresponds to a horizontal scoot. And since it's -4, I know that's going to be a scoot to the right by 4. The -2 outside the function, I need to know that results in a vertical shift. Since it's outside the base function square root of x, it's not in there next to the x, it's outside of it. That's going to result in a downward scoot by 2. So it can be helpful to redraw the little sketch here without actually, putting it on a coordinate plane yet, and just saying, okay, what is this new little origin point? Because it's going to be real helpful if I know where to start it. Well, if I'm going right by 4, the 0, that's going to be the same as adding 4, going to the right of 0 by 4. So the x value is a +4, but now I'm going down for the y value, so that's going to be a -2. Okay, now a graph. And you notice I'm only putting like the necessary amount of tick marks. I mean, you can do that too, right? All I need is 1, 2, 3, 4 in the x direction and 1, 2 in the negative y direction there. That point is going to be, well, right here that's the 4, -2. And by the way, what is the shape of this graph? What is the shape of this graph? That, right? Still points up, and it will cross the x-axis. There's no asymptote stuff going on with these graphs, right? The only ones that have asymptote behavior is the 1/x stuff. So eventually it will cross the x-axis, and maybe I'll just kind of draw it like that. Maybe I should have like a bit more of a curve to it. But again, the point is to get the general shape, get that initial point, right? So that shows that you know it was scooted right by 4 and down by 2, and then get the general shape of it after that. By the way, looking at this picture, what is the domain of this function? I'm bringing domain back up because we're talking about a square root function again. From our work from 2.1, I know that to find the domain of a square root function, I take whatever is inside the radical and I set it greater than or equal to 0, and I solve for x, right? And then I place that inside of a interval like that, right? That's the domain. But I can also see it from my picture. It never goes to the left of 4, right? So I can see from the picture that the domain is 4 to infinity. And its range, which is the y values that it outputs, its range is going to be -2 to infinity. All of these positive values above -2, all the y values, it never goes below a -2 in the y values. It's going to hit -2 is going to be the smallest y value it hits. Everything beyond that is above. That's called the range. The range is the allowable I'll say it this way, is the set of outputs. So what other functions do we deal with that also have restricted ranges besides these square root of x functions? Well, like here, this x squared does, right? It has a restricted range. What's the domain and range of this function? Well, its domain is completely unbounded. You can plug whatever you want into an x squared function, no problem, as long as it's a real number. But its range it is restricted for the y values. You notice, right? Because it never goes lower than 1. It's never going to hit like y equals -5 because it starts at a y value of 1 and then they just go up. So we would say 1 to infinity. Also, where are they? All the way back to the reciprocal functions. What is the domain and range of these functions? Well, the domain is the set of x values that are allowed, and I'm not allowed to plug a 0 into this function. So remember, when we talk about just popping a hole in the domain, you have to write it in this weird way where you don't include that number by these two open intervals and then taking the union of them. So we talked about that. We didn't talk about range, but it's actually going to be the exact same because what's the one y value that this function can never hit? It's that 0 value on the x-axis. The y equals 0 along, it's never going to hit that number either. So it's a set of allowable outputs is actually also going to be excluding 0, every number except for 0. Now contrast that with this function. The even one, its domain is the same, still can't plug in 0, so I gotta go all the way up to 0 and then union it with the other side, right? But what about its range? Well, this one is almost like this odd function in that it can't get 0 because it has that asymptote down here as well, the horizontal asymptote, so it's never going to hit 0, but it's never going to go into the negatives either. Like this odd function, the odd reciprocal function, is allowed to go into the negative y values. This one is not. So this one's only going to get half of that, what the other one has. It's only going to get 0 to infinity. That's it. No union with the negatives because there are no, so it only gets 0 to infinity. Not including 0 because it will never touch the x-axis, which is where y is equal to 0. It'll never get that, but it can go up to any higher number it wants to. Okay, that's a little bit of a tangent, but that's all right. Okay, so we've talked about that. Now let's see what is next. Or do I want to end there for this section? Have I gotten halfway through? I think so. Okay, I'm going to end it there for 2.6. We'll finish 2.6 on Friday.